is Deep Time Detective, and today we're solving a mystery: Earth's heartbeat.
I want you to close your eyes for a second and imagine the deepest, most rhythmic sound you possibly can. Think of a slow, massive, geological heartbeat. Because believe it or not, for over 2 million years, our planet has had a beating heart of ice and fire. It pulses with this unstoppable rhythm that has literally shaped the ground right beneath our feet. Today, we're going to explore the incredible astronomical clockwork that drives our planet, and we'll dive into a mystery that's been haunting climate scientists for a century.
Right off the bat, we need to shatter a pretty common illusion, the illusion of stability. You have never experienced true permanence. It's a heavy thought, right? But think about this. Just 20,000 years ago, the exact spot where Chicago stands today was crushed beneath a solid wall of ice 2 kilometers thick. Mammoths were literally roaming where Manhattan's skyscrapers are right now. And humans? We are walking from London to Paris across a massive frozen grassland known as Doggerland. The world as you and I know it is incredibly temporary.
To actually wrap our heads around why this is, we have to understand what an interglacial period is. So Earth has this pulse, right? It swings from a hothouse to an icehouse. And for the last million years, that pulse has beaten exactly once every 100,000 years. It's a brutal cycle. You get 90,000 grueling years of advancing ice, and that's followed by a really brief 10,000-year window of warmth. We just happen to be living right in the middle of one of those temporary, warm little epochs.
Okay, so how do we actually know all this? This is where the planetary detective work kicks in. Way back in the 1830s, a Swiss naturalist named Louis Agassiz was looking at these long parallel striations scraped deep into bedrock, and it hit him. Only moving ice, literally miles thick, could have carved the world up like that.
But the real smoking gun, that wasn't found until the 1960s. Scientists started drilling way down into the seafloor, and they pulled up these sediment cores packed with tiny calcium carbonate plankton skeletons called foraminifera. These microscopic little shells are basically the planet's black boxes. They carry a distinct chemical fingerprint of what the ocean's temperature and ice volume looked like millions of years ago. Here's how that crazy recording system actually works. When the planet freezes, it traps light oxygen, oxygen-16, inside those massive ice sheets. Because all that light oxygen is locked up in the ice, the ocean gets left behind, totally enriched with heavy oxygen-18. And those tiny shells, they record that exact ratio, which scientists call delta O18. By reading that fingerprint, scientists managed to build this incredibly high-resolution map of Earth's climate history. And you know what? It completely proved in 1976 landmark paper by a mathematician named Milankovitch titled Pacemaker of the Ice Ages. Basically, it proved that climate isn't just random chance.
So if the climate isn't random, what is it? Well, it's geometry. Let's look at the immense clockwork mechanisms that actually drive these massive planetary cycles.
These gears are called the Milankovitch Cycles, and there are 3 major ones that dictate exactly how sunlight hits our planet. First up is obliquity or tilt. Every 41,000 years, Earth's tilt shifts just a bit, from 22.1 to 24.5 degrees, which completely alters our seasons. Second is precession. Think of a slowing spinning top. Our axis does this 26,000-year wobble that shifts our seasonal intensity. And finally, eccentricity. Over a 100,000-year cycle, the actual shape of Earth's orbit gets squashed, shifting from nearly a perfect circle into an ellipse. So the Earth tilts, wobbles, and squashes its way through space. And this brings us to the great 100,000-year problem. It's a massive paradox. Of those 3 cycles, the tilt and the wobble change the amount of sunlight we get way more than the squash does. Eccentricity is technically the absolute weakest gear in the entire clock. Yet, as we just saw, the dominant beat of our planet's pulse for the last million years has been exactly 100,000 years. So how on earth does the weakest force completely dominate the Earth's climate?
The answer lies in something called nonlinear dynamics and the ice albedo feedback. Look, the Earth isn't just sitting there passively taking in sunlight. As ice starts to grow, it acts like a giant mirror, reflecting 90% of sunlight right back into space, which cools the planet even more. These colossal ice sheets build up this immense inertia over 90,000 years. They get so ridiculously thick and stubborn that they just shrug off the smaller melting cycles. But eventually, when all 3 of those Milankovitch cycles perfectly align to blast us with a super strong summer, boom, that towering, unstable ice sheet hits a tipping point and it collapses in a geologic heartbeat, just 10,000 years.
All right, so we've solved how the pulse works today, but there's a massive, glaring anomaly hiding in the deep past.
Geologists have a name for this turning point,
They call it the Mid-Pleistocene Transition. See, before 900,000 years ago, Earth actually followed that faster 41,000-year tilt cycle perfectly. The pulse was quick, and the ice ages were a lot milder. But then, the old clockwork just broke. The planet's heart literally skipped a beat. After that 900,000-year mark, it locked into that slow, heavy 100,000-year pulse, bringing on vastly deeper and way more violent ice ages. What could possibly cause an entire planet to shift its rhythm that drastically?
The first huge hypothesis for this is all about carbon dioxide. Think of CO2 as the planet's volume knob. It doesn't actually trigger the ice ages, the orbital geometry does that, but CO2 totally amplifies the effect. Scientists think that atmospheric CO2 dropped to a supercritical threshold of about 180 parts per million around this era, and that's largely because colder oceans were simply able to absorb way more of the gas.
But how did the CO2 drop that low in the first place? Well, the culprit might be this wild mechanism called the biological pump. During these really cold, dry ice ages, you had these bare, massive plains that whipped up continent-sized dust storms. This wind-blown dust was packed with iron, and when it finally settled over the Southern Ocean, it acted like a giant dose of fertilizer, causing billions upon billions of tiny phytoplankton to bloom. When those plankton died, they sank to the bottom of the deep ocean, physically dragging carbon straight out of the atmosphere with them. With almost no CO2 left in the air, the Earth became hypersensitive to that weak 100,000-year eccentricity cycle.
No, there is a second idea too, the regolith theory. Regolith is basically just the loose soil and rocky debris covering the continents. The theory here is that all those previous, faster ice ages eventually acted like sandpaper, scraping all that loose debris completely off the northern hemisphere. Once the ice was sitting right on the hard bedrock beneath, it could grip better and slide a bit easier without crumbling, which allowed the ice sheets to grow massively thicker. And that extra weight and friction, it created the physical lag and resonance you'd need to force that longer, heavier 100,000-year pulse. Okay, so now that we've mapped out this absolutely staggering timeline of deep time, where do we fit into this giant machine?
The truth is, we are all children of the Interglacial. Every single thing we call human civilization, agriculture, writing, cities, modern science, every bit of it was built entirely within a tiny 11,700-year window since the last ice age packed it up and ended. Our nice, stable modern world, it's literally just a brief intermission. In fact, if you look strictly at those orbital cycles we just went over, our time is technically up. Based on the math, we should be seeing snow continuously accumulating in northern Canada right this very minute, signaling the start of the next ice age due in about 1,000 to 5,000 years.
But we aren't seeing that at all. And the reason why comes down to one absolutely staggering number: 50%. By digging up and burning 300-million-year-old carbon that was left behind by the Earth's very first forests, humanity has increased atmospheric CO2 by 50% in a mere 2 centuries.
When you look at this whole timeline, the profound impact of our emissions is just mind-blowing. We haven't just warmed the planet up a bit, we have accidentally halted a literal geological force of nature. Because of our carbon footprint, climate models are now showing that the next scheduled ice age has been postponed for at least 50,000 years. We literally broke the clock. We are forcing the climate to change 100 times faster than its natural pulse, rocketing us toward temperatures the Earth hasn't felt in 3 million years. And that is far, far faster than any ecosystem can possibly adapt. I want to leave you with a final, profound thought to take away from this explainer today. Dominance is an illusion. Permanence is a fantasy. The rocks remember. When you really zoom out, our planet is fundamentally an ice world. It is capable of dramatic swings, completely indifferent to the human experience. We are simply holding the throne during a brief, warm intermission. The ice that carved the valleys we live in will eventually return. The rhythm of deep time will go on. The only question is, are we truly ready to face the consequences of breaking the Earth's pulse?
If you enjoyed this journey through deep time, like, share, and subscribe, and join us